Okay, so I want you to picture this. In just a single year, the FDA reported more than 370,000 serious adverse drug events, and over 63,000 of those recorded events actually resulted in death. Just think about that massive number for a second. That is 370,000 times where a legally prescribed, heavily tested, and carefully administered medication caused a life-threatening emergency, a hospitalization, or worse. How does that even happen? What if the medicine sitting in your cabinet right now, literally the exact same pill your neighbor takes with absolutely no problem, has a radically different, potentially dangerous effect on you simply because of who you are?
To figure out what's really going on behind this staggering statistic, we're diving into an absolute goldmine of a medical text. It's an investigative tool used by professionals to solve these exact puzzles. We're drawing directly from the second edition of the Handbook of Drug Interactions, a clinical and forensic guide. This book is basically our definitive roadmap into the complex and mostly unseen world of forensic toxicology. It breaks down the exact mechanisms of why our bodies react the way they do and how medical detectives figure out what went wrong when routine treatments suddenly turn fatal.
Which brings us to the central medical mystery we're going to unravel today. Why does a standard drug dose heal one person but harm another? For decades, right, medicine just operated on this massive assumption. We relied really heavily on a one-size-fits-all model, basically believing that a standard dose for a certain weight and age would universally give you a standard result. But as we'll see throughout this explainer, the true answer to this question is actually deeply hidden within the microscopic variations of our own DNA, combined with the incredibly powerful external choices we make every single day.
Welcome to this explainer on personalized justice, the molecular autopsy. Today, we're exploring the fascinating and honestly high-stakes intersection of genetics and forensic toxicology. We're going to uncover how microscopic, completely invisible variations inside your body can turn a perfectly standard, well-intentioned prescription into a fatal dose. We'll also dive into how forensic scientists and toxicologists use this genetic data to piece together post-mortem puzzles, solving real-world medical mysteries that physical evidence alone just can't explain. Here's our roadmap for today. We'll start with the molecular autopsy, move into your genetic metabolic profile, look at some forensic mysteries of opioids, shift over to benzodiazepines in the brain, and wrap up with deadly drug interactions.
Section 1. The Molecular Autopsy, Uncovering the Hidden Suspects. So there's this term coined by Dr. Stephen H. Wong, the molecular autopsy, and it represents a massive paradigm-shifting leap in forensic science. Imagine a scenario where someone dies after taking a completely conventional therapeutic dose of a medication. In the past, traditional autopsies, just looking at the physical organs, might come up entirely empty-handed. But now scientists know they can't just look at the physical body, they have to look deeply into the genome. They use pharmacogenomics, which is the study of how genes affect a person's response to drugs, to explain how the deceased's highly specific genetic code contributed to a drug's fatal toxicity. They are literally dusting for fingerprints on a person's DNA. Actually, scratch that, it's more like they're reading the exact biological instruction manual that person was built with.
To make sense of how a drug goes wrong, you kind of have to divide the suspects into two broad buckets, intrinsic and extrinsic factors. Intrinsic factors are the baseline differences built right into your biology. These are things you generally can't change. Your genetics, your age, your gender, or underlying issues like kidney disease that might slow down how you filter toxins. Extrinsic factors, on the other hand, are the outside influences acting upon your body. This includes your daily diet, physician variability in how they prescribe, and a major one called polypharmacy. Polypharmacy is simply taking multiple drugs at once. For example, casually combining a standard prescription with some over-the-counter cold medicine you grab from the pharmacy aisle. Both of these categories can drastically alter how your body metabolizes a drug.
Let's move on to Section 2, your genetic metabolic profile, the cytochrome P450 enzymes. A really huge part of how you handle drugs comes down to specific biological machinery in your liver called the cytochrome P450 enzymes. Think of enzymes like one called CYP2D6 as a highly specialized factory assembly line designed to break down chemicals. Now, based on your genetics, your personal factory falls into one of four distinct phenotypes. Extensive metabolizers are the baseline. Your assembly line runs smoothly at a standard pace, meaning standard doses work perfectly for you.
Poor metabolizers are kind of like a backed-up assembly line. They lack active alleles, meaning the machine is broken. The original parent drug just isn't broken down, so it builds up and up in the bloodstream until it hits highly toxic levels. Then you have intermediate metabolizers. They have one active allele, so their factory runs, but it's really sluggish and requires carefully lowered doses. And finally, ultra-rapid metabolizers. These are essentially an engine stuck in overdrive. Because they have multiple active alleles, they aggressively and rapidly convert a drug into an active metabolite. That sudden flood of the chemically altered drug can be incredibly dangerous, overwhelming the body's systems in a matter of hours.
Section 3. Forensic Mysteries of Opioids, Real-World Cases.
Let's look at a thoroughly documented forensic case to see exactly how these intrinsic genetics play out in the real world. And fair warning, this is absolutely heartbreaking. A mother of a newborn was prescribed a standard, perfectly normal dose of codeine to manage her pain. But, entirely unbeknownst to her or her doctor, she was an ultra-rapid metabolizer. Her body possessed a duplicated CYP2D6 gene. Her internal engine was in complete overdrive, hyper-converting that standard codeine dose into massive, totally unexpected amounts of morphine. That highly potent morphine then concentrated in her breast milk. Tragically, when she fed her baby, her breastfed infant suffered a fatal opioid intoxication. A completely standard dose was turned lethal, solely because of the mother's invisible genetic code.
The source text also contrasts two different cases involving 3-year-old twin boys, and it really highlights the terrifying invisibility of these mutations. In twin set A, the boys were extensive metabolizers, so genetically normal. Their tragic overdose was due entirely to an extrinsic human error. Their mother was instructed to give them medication in drops, which is an incredibly imprecise measurement technique that accidentally resulted in a massive acute overdose. In sharp contrast, twin set B received the exact correct dose, meticulously measured out. However, they were intermediate metabolizers. They carried a non-functional genetic mutation. Because their biological assembly lines were so incredibly sluggish, their bodies just couldn't clear the medicine efficiently. Over a few days, the standard dose of codeine compounded, quietly building up to toxic, fatal levels. Extrinsic error versus intrinsic mutation. In both cases, loving parents thought they were doing the exact right thing, which just shows why genetic awareness is quite literally a matter of life and death.
Pivoting now to Section 4, Benzodiazepines and the Brain, Shifting the Focus.
Benzodiazepines are everywhere in modern medicine. You likely know someone who takes them, or hey, perhaps there's a prescription sitting in your household medicine cabinet right now. Because of their really profound sedative effects on the central nervous system, they're commonly prescribed all over the world to treat acute anxiety, manage severe insomnia, provide crucial sedation before medical surgeries, and even act as emergency control for epilepsy and violent seizures. But how do these incredibly common little pills actually manage to calm the complex human brain down?
Well, according to our authoritative source text from Humana Press, we can think of a specific amino acid called GABA as your brain's natural brake pedal. Its whole job is to slow things down. Benzodiazepines essentially step really heavily on that natural brake pedal. They bind directly to the GABA-A receptor, which acts like a locked gate, specifically a chloride channel, in the brain's membrane. When the drug binds, it forces those chloride channels wide open. This physically floods the system with a chloride current, slamming the brakes on your central nervous system. It physically and chemically slows the brain's rapid-fire electrical signals to a crawl.
Finally, Section 5. Deadly Drug Interactions, when extrinsic factors turn fatal.
So we've explored the intrinsic genetic side. Now let's look at the extrinsic side. The most dangerous interactions with central nervous system depressants are what we call pharmacodynamic, meaning how the drugs physically team up against your body. Because benzodiazepines step on the brain's brake pedal. Combining them with other depressants, like opioids, barbiturates, or even just alcohol from a casual night out, creates a devastating compounding effect. They stack right on top of each other. The brain's electrical signals get slowed down so aggressively that the body simply forgets an involuntary function, breathing. This fatal respiratory depression is a leading cause of accidental, entirely preventable overdoses worldwide.
Now, you might think the greatest danger is mixing handfuls of pills, but sometimes the real culprit is sitting right there on your breakfast table. Interactions can also be pharmacokinetic, meaning outside substances hijack how your biological factory actually operates. Enter the grapefruit juice surprise. Drinking a standard glass of grapefruit juice acts as a remarkably potent inhibitor of the CYP3A4 enzyme in your liver. It literally blocks the very enzymes responsible for clearing drugs out of your system, shutting down that assembly line entirely.
Let's look at the terrifying real-world consequence of this breakfast table interaction.
A powerful synthetic opioid like fentanyl is heavily metabolized and cleared out by that exact CYP3A4 enzyme. If a patient takes an inhibitor, whether that's a prescribed antifungal medication or simply drinking a glass of grapefruit juice, that enzyme is blocked from doing its job. The fentanyl cannot be cleared, so it lingers, stacking up dose after dose, leading to a deadly, toxic buildup in the bloodstream. And the crazy part, this happens even if the patient's intrinsic genetics are completely 100% normal. It's a chilling reminder that extrinsic choices at the breakfast table can completely override your baseline biology.
As the molecular autopsy continues to mature and evolve, it reveals just how profoundly our individual DNA and our daily environments dictate our medical outcomes. The variables are just astronomical. So we really have to ask ourselves, is the era of the one-size-fits-all prescription finally over? The emerging science of personalized medicine and personalized justice when things go wrong tells us it absolutely has to be. Thank you so much for joining me for this explainer. And remember, always question the science behind the prescription.